In Chapter 4, we're going to hit on just two sections really to talk about the basics of probability because these are important for statistics. Probability is really important as we move on to inferential statistics. So far we've been doing descriptive statistics where you just do calculations on the sample itself. Now when you move into inferential statistics, you say, based on this sample and what I've figured out, what do I know about the whole population? But that's where the probability comes in, because if you think about it, you can't be 100% sure what's going on in the population just by looking at a small sample, right? So if I look at 10 people in the class and do a survey, I can assume that those results would be similar to everyone in the class, but I can't be 100% sure that if 10% of my sample like bananas, that when I go and look at the whole class, is it still going to be 10%? Well, probably not exactly, but probability will help me figure out how close to that 10% it would probably be. Therefore, statisticians think in probabilities, and what we want to know is what is pretty sure to happen. We'll never be 100% sure, but we can be mostly sure, and that's good enough for a statistician. If something has a very, very small probability, then we're pretty sure that it's not going to happen, and that's how what we base a lot of our statistics on. So a little bit of new vocabulary. An event is something that you want to see happen in probabilities. It's the thing that you're trying to find the probability of. And then there are also simple events that are just one component. And we're going to talk more about event versus simple event in a minute. And then there's a sample space, which is all of the possible events that could happen. And we're going to talk more about that too. Okay, so simple event versus event. A simple event can only happen one way. So for example, when I'm rolling one die, which is the singular of dice, there's only one way it can happen. I either roll a 5 or I don't. But if you have 2 dice, you can roll 5 in some different ways. You could get a 1 and a 4, you could get a 2 and a 3. So that would not be a simple event because it can happen in 2 different ways. A sample space is a list of all the different things that could happen. So if I'm rolling one 6-sided die, then the sample space would be that I could roll a 1, 2, 3, 4, 5, or 6. But sometimes sample spaces are a little more complicated. So let's look at an example where you're looking at a family with 2 children and you want to know the different combinations of boy versus girl that could happen in this family. Sometimes it helps to draw a tree diagram to sort these things out. You wouldn't have to do this, but it can help. So the tree diagram says that first we're going to look at what could happen for the first child. Well, the first child could either be a boy or a girl. And then we go up to the top and say, okay, what if that first child was a boy? Then the second child could still either be a boy or a girl. And same thing if the girl were the first child, then the next child could either be a boy or a girl. And then you can follow the tree up the different branches to get the different combinations. We could have a boy and then a boy. We could have a boy and then a girl. We could have a girl and then a boy. We could have a girl and then a girl. So there are 4 different possibilities. Notice that boy-girl and girl-boy are separate possibilities. We don't just say we could have one of each. It makes a difference. It could be that the oldest is a boy and the youngest is a girl, or the oldest could be a girl and the youngest could be a boy. So our sample space has 4 different possible combinations. Now what we're usually interested in is, out of those possible combinations, what's the probability of a particular one happening? And the notation that we use for that, we use capital letters to stand for the things that we want to have happen, and then we say probability of that by putting P and then parentheses and then what we want to have happen inside the parentheses. So there are 2 ways to write these. One thing I could do is say that capital A stands for having 2 girls, and then I could just say probability of A. Or, as you can see here, instead of doing that, I've said the probability of 2 girls and I've written girl girl, or just say 2 girls. So those are both ways that I could write the probability of 2 girls. Now, probabilities are always between 0 and 1, or you could think of that as 0% and 100%. But probabilities can be written as both decimals and percentages. For example, 0.52 would be 52%. So if we're thinking of these in decimals, 0% is 0, 100% is 1. And so the probability being 0 means there's no chance at all. Probability of 1 means 100% chance, definitely going to happen. Most of the time the probabilities are somewhere in the middle. Now when we're working with means and standard deviations, we have the range rule of thumb to tell us when things are unusual. When we're working with probabilities, we don't have that. So in general, we will consider something to be unusual if the probability is less than 5%. And then it's rare if it's less than 0.1%. Now sometimes a problem may specify different cutoffs for unusual, but these are sort of general common ones to use. We round a little different when we're calculating probabilities. With means and standard deviations, we need to be careful that we don't make something more precise than we're really able to know. But with probabilities, we don't have that issue, so the more decimal places, the better, with a minimum of 3 significant digits. So that's different from 3 decimal places. Zeros at the beginning don't count. I'll give you a couple examples of that. So if we're dealing with 2 out of 3 and you get 0.6 repeating, then you're going to go ahead and round to 3 decimal places. That'll round up to 0.667. However, if you're dealing with something like the second example where there are zeros at the beginning, you don't actually start counting the 3 digits until you get to the first number that's not 0. So in that one you'd round to 0.00408. And then similar on the next one, it would round to 0.0551. Be careful that you round up when the next digit is 5 or larger. Okay, so where do these probabilities actually come from? Well, there are 3 different ways that probabilities get calculated: relative frequency, classical approach, and subjective, and we'll talk about each of these. The relative frequency approach is based on things that have actually happened. So we look at the number of times something happened out of how many times you tried it, and then that will calculate an approximate probability. So we use this approach when we're working with sample data, something that actually happened, or if it's some sort of probability that's hard to calculate in theory, so we just look at how many times something actually happened. And because it's based on real life things happening, it's actually just an estimate of the theoretical probability. Even though it's just an estimate, the law of large numbers says the more times you try something, the closer your actual results will get to the theoretical probability. You'll be more accurate if you try something a whole bunch of times. So for example, if you're flipping a coin, you expect to have a 50-50 chance of getting heads or tails. But if you flip it 3 or 4 times, you wouldn't be surprised if it didn't come out exactly 50-50. But the more times you flip the coin, the closer you would get to 50-50. So for example, you want to estimate the probability of a 25-year-old man dying before his 26th birthday. So we look at men aged 25. We find out that out of 100,000 of them, 138 died within the next year. So we'll use that information to estimate this person's chance of dying. So we pick out the key pieces of information. I'm going to let A stand for 25-year-old man dying before he turns 26 so that I don't have to write that out every time. And this has happened 138 times out of 100,000 total. So I say the probability of A, which stood for 25-year-old man dying before he turns 26, would be approximately 138 out of 100,000, which comes out to 0.00138. So if I were to change that to a percentage, I'd move the decimal point 2 places to the right. That would be 0.138% chance of a 25-year-old man dying before they turn 26. So very small chance. Another quick example, if you look at the first 42 presidents, 26 of them were lawyers. So we're going to calculate the probability if you were to randomly select one of those presidents. What's the chance of choosing a lawyer? Let A stand for what we're looking at and pull out the key pieces of information. And the chance is 26 out of 42. You can either reduce that fraction to 13/21, or you can go ahead and change it to a decimal and round it to 0.619. Or you can even write it as 61.9%. I will take any of those 3 forms. Now in this particular case, this is actually an exact probability because we only asked what's the chance of getting one of those 42 to be a lawyer. It's an approximate probability if I said based on that, what's the chance out of all the presidents of picking a lawyer? So that would be an estimate if I extrapolate it out to a bigger group. And then one more example, let's say we do a quality control test. We've got 5 defective printers and 15 that are good. We want the probability of choosing one that's defective. Be careful on this one when you pull out the key pieces of information because we've got 5 defectives and 15 that are good. That means we're actually working with 20 printers total, and that's important. So the probability of choosing one that's defective would be 5 out of 20, which I could write as 1/4, or I can write it as 0.25. Now with probabilities, if they come out exactly to less than 3 decimal places, we do not need to add that extra 0 on the end to get it up to 3. I can just write it as 0.25 or 25%. Now a lot of the times in a math class though, we're calculating our probabilities theoretically using the classical approach or the theoretical approach, where we actually figure out in the sample space how many things are in the sample space, and then we count how many of them do what we want, and then calculate our probability that way. So we've looked at 2-child families and the different combinations of boy versus girl. Let's find the probability of having 2 boys if you have 2 children. So we've already done the tree and figured out the 4 different possibilities in this case, so we'll go ahead and just use those. We've got the sample space. There are 4 possibilities in the sample space. Only one of those has 2 boys in it. So our probability would be 1 out of 4 or 0.25. So let's try another one where we don't have to find the sample space, it's just given to you, some made up sample space. So in this group of possible combinations, what's the probability of getting an event that has at least 2 A's in it? And then what's the probability of getting an event with no C's at all? So on that first question, probability of at least 2 A's, let's keep in mind that at least 2 means 2 or more. So you count how many of those had 2 A's or more than that. There were 8 combinations in the list. 5 of them had 2 A's or more than that, 3 A's, 4 A's. So you can leave it as 5 out of 8, or you can divide and make that a decimal, or you can write that as a percentage. Part B, probability of an event with no C's. We count that there are 3 different combinations that don't have any C's in them. And so we've got a 3 out of 8 chance. We can leave that as a fraction, or we can change that to a decimal or percent. Now there's one last way of calculating probabilities. These are called subjective probabilities, and this is the probability of an event estimated on some sort of knowledge of relevant circumstances and a little bit of guesswork, informed guesswork. This includes things like weather prediction, where a lot of different things as well as a little bit of experience and intuition come into play, and we will not be dealing with these in this class.